In this video, we will be learning how to write complete ionic equations and net ionic equations. This is part of our learning objective for learning how to represent chemical reactions with chemical equations. Before we get started, we really need to review what cations and anions make up ionic compounds. And so I want you to pause the video and try to determine what the cation and anion are that make up the following ionic compounds. Unpause the video when you are ready to double check your work. Okay, so we know that the cation is always listed first in the chemical formula. So the cation will always be the element that's listed first, and the anion will always be listed second. All of our anions have predictable ion charges. NO3 is our polyatomic ion nitrate, which has a 1- charge. There is only one silver here, and so our cation is silver with a +1 charge. For our second compound, our anion is chlorine, and our cation is iron. We have 3 chlorines. Chlorines are in the halogen group, which is a -1 charge. Since we have 3 chlorines and only 1 iron, that means our iron has to be a +3 charge to balance out. For our third one here, we have a cation of sodium and an anion of hydrogen carbonate. Regular carbonate has a 2- charge, but since there's a hydrogen here, that's going to make the charge 1 less. And so now it's only a 1- charge. Sodium is in group 1, and it will be a +1 charge to make this a neutral ionic compound. For our last one, we have calcium and we have oxygen. Oxygen is a 2- anion, and calcium is a 2+ ion, since it's in group 2. The reason why we had to go over that is because when we have ionic compounds dissolved in solution, the cations and anions separate because ionic compounds are strong electrolytes. So any ionic compound would dissociate completely in solution into its separate cation and anion. Non-electrolytes, such as molecular compounds, do not create ions. And weak acids and weak bases are weak electrolytes, meaning that they partially ionize and also partially stay together. Mostly stay together. Since our ionic compounds completely dissociate in solution, then it's more accurate to actually represent aqueous ionic compounds and other aqueous strong electrolytes as separate ions. And so in an earlier video, we talked about writing chemical equations where everything was neutral compounds. And so that's really known as a molecular equation. So when everything is written as neutral compounds, then we call that a molecular equation, even though these things are not molecules. They are ionic compounds. But in solution, these strong electrolytes really exist as separate ions. And so all of the aqueous strong electrolytes will need to be written as ions in a format of chemical equation we call a complete ionic equation. So when we write our same equation down here, all of our aqueous strong electrolytes are written as ions. Everything else is left alone. So do not ionize any solids, do not ionize any liquids, do not ionize any gases, do not ionize any weak electrolytes, and do not ionize non-electrolytes. So the first thing we need to do is determine, well, I'm going to copy down the arrow so that I remember where the arrow is. I'm going to move the arrow into the center. So everything that's on the reactant side will need to stay on the reactant side. Everything on the product side will need to stay on the product side. And since I need to not ionize solids, I can see here that this one's a solid. So I'm just going to copy this down right away before I forget that it's a solid and I should not ionize solids. Next, I have to identify which of these remaining substances I need to ionize. And so to do that, I have to figure out which ones are strong electrolytes. And so anything that's an ionic compound, a strong acid, or a strong base will be a strong electrolyte. So KOH is an ionic compound. And it's also a strong base. All of our strong bases are ionic compounds. So that is a strong electrolyte. Now we have magnesium nitrate. That's also an ionic compound, and so it's also a strong electrolyte. And you can see that all of these are aqueous, and so that's why I am considering to ionize them. And so since it's aqueous and it's a strong electrolyte, they will be ionized. And so that one's ionic as well, strong electrolyte, and so it will be ionized. So I know that much like how we did in our warm-up, I can separate these into the separate cation and anion. And so for my first compound, I have potassium ions and I have hydroxide ions. Those are now separate, so I could put plus sign in between them, but you'll see that they added 2 out in front. That 2 distributes out to both ions. And then since they were both aqueous, that aqueous also applies to both. So we got to remember to distribute those out. Okay, next up we have magnesium and nitrate. Magnesium is magnesium, and that's in group 2, so that's a 2+ charge. And then we have nitrate, which is NO3 with a 1- charge. There were 2 nitrates here, and so that 2 on the outside the parentheses comes out in front to indicate that we now have 2 separate nitrate ions. And then the aqueous also gets distributed out. So both of these ions are aqueous. Now we move over to the product side, and we have 2 potassium nitrates. And so we have that 2 will apply to both the potassium and the nitrate. The aqueous will apply to both as well. So that's going to be 2 potassium ions and 2 nitrate ions that are aqueous. And so now we have finished writing our complete ionic equation. So you can see here that this equation is still balanced. On both sides I still have 2 potassiums, I still have 2 hydroxides, I have 1 magnesium and 2 nitrates. This is just another format for writing an equation for an ionic compound in solution that more accurately represents what's actually in solution. Now, you might have noticed on the previous slide that some of these ions in the complete ionic equation undergo no chemical change whatsoever. So our potassium, for instance, exists as 2 potassium ions, and then after the reaction, there's 2 potassium ions. And so these are what's known as a spectator ion. These spectator ions are just watching the chemical reaction happen without actually doing anything. Same with the nitrates. The nitrates are also spectators. And so we can cross out the spectators to simplify our equation, and then we'll be left with our net ionic equation. The net ionic equation only includes the ions that undergo a chemical change. And so when we write our net ionic equation, it will be 2 hydroxides and 1 magnesium cation form magnesium hydroxide solid. And so this is the actual chemical change that's occurring when we mix these 2 things together. Later we will learn that this is called a precipitation reaction because solids form out of aqueous species. Here's a practice problem for you. go ahead and pause the video and try to write the complete ionic and net ionic equations for the following reactions. Unpause the video when you are ready to continue. Okay, so what I'm going to do first is I'm going to identify any solids, liquids, gases, and non-electrolytes or weak electrolytes in the sample, because those are going to be copied down exactly as is. In this first reaction, I see that this is a solid. And so I know that I'm going to be forming barium sulfate solid. Barium sulfate salt. So I can copy that down directly as is because I know it's a solid and I do not ionize solids. For the rest of it, I have to identify if all of these are aqueous and if they're strong electrolytes. All of the remaining compounds are aqueous, and so now to decide if I'm going to ionize them, I have to see if they are strong electrolytes. This is ionic, and so it is going to be a strong electrolyte. Barium nitrate is also going to be ionic, and potassium nitrate is also going to be ionic. I know that because it's made out of a metal and one of my polyatomic ions. So all of these are going to be strong electrolytes and they're aqueous. So all of these compounds are going to need to be ionized. My first compound will form two separate potassium ions and one sulfate anion. And then that aqueous applies to both. Now I have my barium cation. Barium is a 2+ cation. And now I'm going to have two separate nitrate anions. And then on this side, I have that 2, which is going to distribute out. And so that's going to be 2 potassium ions and 2 nitrate ions. For my net ionic equation, I can take my complete ionic equation and cross out any spectator ions. The spectator ions are the ions that undergo no chemical change. I know I'm trying to form barium sulfate, and so I know that the only ions I should have left are barium and sulfate. So the only ions I should have left are my barium and my sulfate after I cross out my spectators. But let's go ahead and double check. I see 2 potassium ions over here, 2 potassium ions over there, 2 nitrate ions, 2 nitrate ions. And so yes, the only ions I'm left with are barium and sulfate, which is all the ions needed to make barium sulfate. All right, for our bottom reaction, I'm going to go ahead and put in my reaction arrow here. And then I got to figure out which ones I should not ionize. So I see that that one's aqueous, aqueous, aqueous. I know I do not ionize liquids or gases, and so I got to keep the carbon dioxide in water intact. And so I'm going to write CO2 gas and H2O liquid. CO2 gas plus H2O liquid. Now I can go back through and I can figure out if I ionize the remaining compounds. So this one is ionic and it's aqueous, so I am going to ionize this compound. This one is a strong acid and it's aqueous, and so I am going to ionize that one as well. And this one's ionic and it's aqueous, and so I am going to ionize it. And so here, sodium carbonate is going to, that 2 indicates I'm going to have 2 separate sodium ions. And it's going to be aqueous. This is carbonate. Carbonate is going to stay intact as carbonate. Carbonate has a 2- charge. That's not a charge. That was supposed to be my arrow in between. And now I have that 2 distributes out to both the hydrogen and the chlorine. and that's going to be aqueous, aqueous. Now for this, the 2 is going to distribute out to the sodium and the chlorine. So that's 2Na plus and 2Cl minus, aqueous, aqueous. So I can cross out my sodiums because I can see that they don't change. I see 2Cl minus and those don't change. And so what I'm left with on my product side is only the carbon dioxide and water. I'm going to go ahead and move my reaction arrow closer. And then I just need enough room for me to write CO3, 2 minus, aqueous, and 2H plus, aqueous. And so you can see that for my net ionic equation, this is balanced. And so the states of matter just stay the same throughout. It's not like these automatically became aqueous or anything. These stay as gases and liquids. They stay the same state of matter as they were in the other formats of chemical equations because these are all different ways of expressing the chemical change that has occurred. So stay tuned.